All right, in this video, we're going to look at best approximations and how to calculate them. So in the previous video, we looked at two vectors v and w, and we found the scalar multiple of w in this perpendicular vector z. And we realized that if you're given v and w, the best approximation to v in the span of w is cw. Right? So in other words, if you're restricted to staying on the line formed by the vector w, and you can look at any scalar multiple of w to stay in that line, the closest you can get to v, if you're restricted to that line, is c times w. And the way we calculated c was shown in the previous video, but the result was c is just this ratio of dot products. Dot product of v and w divided by the dot product of w with w. So once you do that calculation to find c, then all you have to do is do c times w, and that'll be the closest you can get to v. We also did this in 3 dimensions. Right? If you were given these vectors v, w1, and w2, then we found this linear combination of w1, w2, so c1, w1 plus c2, w2, and this perpendicular vector z. And a very analogous thing, given v, w1, w2, where w1 and w2 are orthogonal, the best approximation to v in the span of w1, w2, so that's a plane as shown in the picture, the best approximation is c1, w1 plus c2, w2. In other words, if you're restricted to that plane formed by all linear combinations of w1, w2, the closest you can get to the vector v is c1, w1 plus c2, w2, and we found how to calculate c1 and c2 before. It's the ratio of the dot products. So there's c1 and there's c2. So we'll apply this knowledge of best approximations, and you'll really want to remember these ratio dot products, and that the best approximation is c1, w1 plus c2, w2 if you're working in the 3-dimensional case, but you can keep going in higher dimensions if you'd like. All right, let's look at an example. So if w1 is the vector 0, 1, 0, and w2 is the vector 1, 0, 1, notice these two vectors are orthogonal. Their dot product is 0. Find the best approximation to v equaling 1, 2, 5. And we have to stay in the span of w1, w2. So we're restricted to all linear combinations of w1, w2. We're trying to find where's the spot that's the closest to the vector v. All right, so all we have to do is calculate c1, w1 plus c2, w2, where c1 and c2 were the calculations that we showed before. Right, and if we do this, that'd be, c1 would be the ratio of the dot products. It's v dotted with w1 divided by w1 dotted with w1 times w1. And we add v dotted with w2 divided by w2 dotted with w2 all times w2. Right, so find the ratio of those dot products, and then we're scaling w1, w2. And that's the closest you can get to v. Actually performing those dot products, you get the first ratio is 2 over 1, the second ratio is 6 over 2. So you can scale and add to get the vector 3, 2, 3. 3, 2, 3 is a linear combination of w1, w2. So it's in the plane spanned by w1, w2. And that's the closest you can get to the vector v. All right, we can apply this idea to find the best fit line to data. So in this graph, we have 3 data points. That definitely doesn't fall on a line, but we're going to find the line that best fits the data. So our equation of a line is y equals mx plus b. I'm writing it as mx plus b is equal to y. This is for a nicer format that we're used to. I'm going to plug in my x and y coordinates. So the first x coordinate is 1, the y coordinate is 0. Next one is the x coordinate of 2, y coordinate of 1. And the third data point is x coordinate of 3 with a y coordinate of 3. And we can write that as a matrix equation, right? Extract the coefficients in front of m and b. Right? The coefficients from m are 1, 2, 3. Coefficients from b are 1, 1, and 1. Right? B is multiplied by 1 each time. And we set that equal to the right-hand side of the equal sign, right? 0, 1, 3. That's our matrix equation. And here you just got to remember the definition of a matrix times a vector. It's a linear combination of the columns using m and b as the weights. So it'd be m times the first column plus b times the second column is equal to the 0, 1, 3 vector. And that's equivalent to our system of equations. Now we already know that 0, 1, 3 is not in the span of the two columns of the matrix, right? There's no way to linearly combine the two columns of our matrix to get 0, 1, 3 because there's no line that perfectly fits those three data points. So we can think of this as finding the closest you can get to 0, 1, 3 while staying in the span of the columns of our matrix, right? Staying in the set of all linear combinations of the vectors 1, 2, 3, and 1, 1, 1. All right, so V1 is 1, 2, 3, V2 is 1, 1, 1, and V3 is 0, 1, 3. Now these, the vectors V1 and V2 are not orthogonal, so we need to come up with an orthogonal set that spans the same space as V1 and V2. Now that's the Gram-Schmidt process that we developed in the last video, so I'm not going to show it all again here. I'm just going to state what the orthogonal vectors would be if you applied the Gram-Schmidt process. So W1 is 1, 2, 3, and W2 is 4, 1, negative 2. Now we have our orthogonal set that spans the same space as the columns of our original matrix. And now we can do the calculation C1 W1 plus C2 W2. Right? So V3 dotted with W1 divided by W1 dotted with W1 all times W1 plus V3 dotted with W2 divided by W2 dotted with W2 times W2. Right? That's the calculation that we were doing before. That gets us closest to our vector V3 in this case. So you can perform those dot products. And the first ratio is 11/14, and the second ratio is negative 5 divided by 21. And if you scale and subtract those two vectors, you'd get the vector negative 1, 6, 4/3, 17 divided by 6. So we haven't solved the problem yet. We just figured out where in our column space of A, in other words, a certain linear combination of the columns of A, that gets us closest to the vector V3. That gets us closest to 0, 1, 3. Now the question is, what value of M and B would actually get us this vector that's closest to V3, right? So we have to solve this new equation. The matrix times MB is equal to that vector that we just solved for, right? We know this definitely has a solution because that red vector is just a linear combination of W1 and W2. And any linear combination of W1 and W2 is in the span of V1 and V2, right? Because that was how Gram-Schmidt process worked. Give us an orthogonal set that spans the same space as our original set of vectors. So you could get the augmented matrix and reduce it to solve for M and B, and you'd get 3/2, negative 5/3. And so M is 3/2 and B is negative 5/3. That'd give you the equation of the line that best fits the data. Now we're going to look at approximating a function f of x using a set of basis functions. So we're going to do what's called finding the least squares approximation. And that'll be g of x equaling a0 plus a1x plus a2x squared of f of x is equal to sine of x on the interval from 0 to pi. So in other words, we're trying to find the best quadratic that fits the function sine of x just on the interval from 0 to pi. To do this, we'll need a basis for P2, that is the set of all polynomials of degree 2. So our standard basis is 1, x, and x squared. That is a basis for P2. But remember, this standard basis is not an orthogonal basis. So we'll have to use the Gram-Schmidt process to come up with an orthogonal basis. And also we'll use this inner product of the integral f times g dx from 0 to pi. So the area under f times g from 0 to pi. That will be our inner product, and we've shown before that that computation satisfies the 4 properties of inner product. So it's the inner product we'll use here because our interval that we're considering is 0 to pi. And you can use the process that we showed in the previous video, the Gram-Schmidt process, to come up with an orthogonal basis. I'll just state it here. An orthogonal basis for P2 using this inner product is 1, 2x minus pi, and 6x squared minus 6 pi x plus pi squared. You can check it out and do the inner product of each pair of those three functions, and you'll get 0 because they're all orthogonal. Now, if you apply the Gram-Schmidt process, you might get slightly different functions. I happen to scale the functions so the numbers are a little nicer. So for example, the second function, 2x minus pi, when I applied the Gram-Schmidt process, I actually had x minus pi halves as the second function, and I just scaled it by 2, so I get 2x minus pi. Right? If you scale one of the vectors, right? In this case, the vectors are functions. If you scale one of the vectors, it's still orthogonal to all the other vectors in this set. So I just made it so the numbers are a little nicer. Now that we have an orthogonal basis, all we have to do is to find the linear combination of these basis vectors, C1W1 plus C2W2 plus C3W3, where C1, C2, and C3 are found by doing the ratio of those inner products that we've done before. All right, so there it is with W1, W2, W3 put in, and the ratio of those inner products for C1, C2, and C3. Remember, we're not doing dot products here. We're doing the more generalized inner product, where the inner product is defined to be the integral of f times g dx from 0 to pi. So each inner product here, you just want to use a calculator and type in the integrals and figure out what those integrals come out to be as a number. And so that's what I did. I computed all those integrals using a calculator. And in the end, when you add that all up, you get negative 0.4x squared plus 1.3x minus 0.1. So the idea is, this is the closest you can get to sine of x, and in closeness we're measuring using this inner product of f times g from 0 to pi. It's the closest you can get using that inner product on the closed interval from 0 to pi when you're restricted to just using polynomial of degree 2. You can't get any closer than that. All right, we'll look at another example here. This time we're finding the least squares approximation g of x, which is a0 plus a1x, of f of x is equal to e to the x on the interval from 0 to 1. In other words, we're trying to find the best line that fits e to the x on the closed interval from 0 to 1. Well, to do this, we need an orthogonal basis for all polynomials of degree 1. And then we can find that linear combination of those basis functions to figure out the best approximation. So our standard basis is 1 and x. Right? All linear combinations of 1 and x would give you any line you'd like, any polynomial of degree 1. So that is a basis for P1. And we'll use the inner product, the integral f times g dx from 0 to 1. So that'll be our inner product in this case, because our interval that we're concerned about is 0 to 1. Now using the Gram-Schmidt process, we can find the orthogonal basis. That would be 1 and x minus a half. You can verify my math there by doing the Gram-Schmidt process, or just checking the inner product and making sure that it is 0. That means that they're orthogonal. Now that we have an orthogonal basis, all we have to do is find that linear combination of those two functions. So C1W1 plus C2W2, right, where C1 and C2, those ratio of inner products. So there we go. There is. We can rewrite those inner products as what they are defined to be, right? Those integrals from 0 to 1 of the product of the functions given in the inner product. And I used a calculator to figure out all those integrals. And in the end, after using my calculator for the integrals, I get the function 1.7x plus 0.9, approximately. I'm rounding to 1 decimal place here. So out of all possible lines, this is the best line. It's the closest one to the function e to the x using this inner product, the integral of f times g from 0 to 1. All right, that's pretty neat. We got the best line for e to the x on the interval from 0 to 1. All right, that's it for this video. Thank you.